right, folks, now let's start doing some real optimization problems, real-life optimization problems. This is one very popular that I call the fence problem, where you want to maximize the area of a fenced-off field. Okay? It says you want to enclose a rectangular field with a fence. So let's draw a rectangle here. So you got a rectangular field, and we want to enclose it with a fence. And we don't know what the dimensions are going to be. You have 800 feet of fencing, and one side of the field already has a fence. So really all we have to do is, this problem is telling us, it says, so you won't need fencing on one side. So one of the sides of the fence, or one side of the field, already has a fence. So all we have to do is put fencing on this side, and this side. We only have to do 3 sides of the field to fence it in, because we're extending the fence along another fence. It says, what are the dimensions of the largest area that you can enclose with the given material? Okay, well, what are the dimensions of the largest area? So it says, identify a formula for what is being maximized or minimized. Well, we're looking for the largest area, and therefore we're maximizing area. Area of what? Well, we're enclosing a rectangular field. So we are maximizing the area of a rectangle. And so our formula for step 1 is going to be the area of a rectangle, which is length times width, or base times width, or whatever. It doesn't matter. It's just two linear dimensions, okay? But now we have a problem, because it says, because we have 2 input variables, length and width. So we got to try and come up with some kind of formula that relates length and width to each other. Now, thankfully, length and width are related to each other. And if you look at the question, it says that we're going to enclose this field with 800 feet of fencing. Well, where does the fencing go? The fencing goes around the outside of the rectangle, right? And that is the perimeter of the rectangle. So I know that perimeter is related to length and width. So if we say that perimeter is equal to 2 times, well, really it's length plus width. So that's 2 lengths plus 2 widths, right? And so this relates it, but this is a problem now, because we are introducing even another variable. So we can't really, we can use perimeter, but we can't use it as it is. We need to fill in for perimeter, or we need to fill in for length and width. Now here's the funny thing, is we have 800 feet of fencing that has to go around 3 sides. So let's say that this is a length, and this is a length, and this is a width, and this is a width. And since we only have to go around 3 sides, we can say that the 2 widths and one of the lengths is going to be equal to how much fencing we have, 800 feet. So instead of saying 2 lengths, we're going to change this. What we really have is we have 800 feet of fencing, and that's going to be equal to 1 length, so that's length, plus 2 widths. And now, if we subtract 2w from both sides, what we now have is length is equal to 800 minus 2w. And so now we have a formula, we have another equation that relates length and width to each other. So now what we'll do is we'll go over here for step 2, and we'll substitute, we'll take out length, and we'll put in 800 minus 2w. So area is going to be equal to 800 minus 2w times w. And now we can distribute the w. And if we distribute the w, we get area is equal to 800 w minus 2w squared. And now we have an area formula. That's step 2. Now, we're going to identify the interval of input values if they are relevant. Well, so now we are going to have an interval. Because if you look at this formula right here, first of all, width cannot be negative. We can't have a negative width on the region. So we know that on the lower end that the interval can only be as small as 0 because a geometric dimension can't be negative. It has to be positive values, or it can be 0. So we're going to start at 0, and then, well, how long can the width be? Well, one thing you can do is, if the length is 0, let's assume that the length is 0, we still need 2 widths. And what that means is we have to split the 800 feet between 2 widths. We have 2 of them, so they both have to be represented. And that means that the longest that width can possibly be is 400. Because if this one's 400, then we need the other 400 feet of fencing for the other W. So our interval is from 0 to 400, okay? So now, this is a situation where we needed to use step 3. So we know that our interval is from 0 to 400. And so now the last thing we're going to do is we're going to optimize the function using the procedure we learned in optimization 1. And basically what we do is we create a table with the W values and with the area values. And the first thing we're going to do is we're going to put in the endpoints from 0 to 400. And now we're going to see if we have any critical values. And the way we find the critical values is we do the derivative of our formula. This is our new area formula. And the derivative, A prime, is equal to, the derivative of 800W is 800, minus the derivative of 2W to the second power is 4W. And now we'll set this equal to 0. If we set this equal to 0 and solve for W, we get 200. Okay, because 4 times 200 is 800, and 800 minus 800 is 0. So we know that the only critical value, excuse me, that's not W. The only critical value on W is 200, or on A is 200. Now we plug each one of these numbers into this area function. If I put a 0 in, I get 0 minus 0, that's 0. If I put a 400 in, 400 squared is a really big number. Hang on a second here. Okay, so this would be 2 times 400 times 400. Well, 2 times 400 is 800. And then 800 times 400 is equal to 800 times 400. So if we were to plug 400 in, we would also get 0. So I'm pretty sure those are not going to be the answers. But now we're going to put 200 in. And let me find a calculator around here. Here's one. So if I do 800 minus times 200 minus 2 times 200 squared, I get 80,000. And that is a larger number than 0 or 0, right? So this is our maximum. And therefore, our width is going to be 200. And now to find out what the length is going to be, to find the dimensions of the largest area, all I need to do is go back to the length formula, 800 minus 2W, and put 200 in. 2 times 200, that's 400. 800 minus 400 is 400. And so the field of maximum area, given the fencing that we have, is a 200 by 400 field. A 200 foot by 400 foot field. Okay? And that is the fence problem.